Well, good afternoon, everyone, and welcome to another exciting lecture in computer architecture. I'm thinking this is going to be the last class of the semester for many of you, unless you've got a class on Friday or something like this. And so it's kind of got mixed feelings about this one. The last class of the semester. Wow. Uh, let's review a little bit about what we have coming up. There's a final, and it is due on the 17th. Today is the 10th, so that means you've got one more week to go on the final. What I thought I would do is take a little time today and make sure that we are up to speed on the final. And so what I would do, I think, is just kind of scroll through the final, and if there's any kind of question about any of the questions on the final, you should stop me and ask me a question. Otherwise, I'm just going to zip through the final if that's okay with people. Just because I think we don't want to wait till the last minute to find out we don't understand something. So unless somebody wants to stop me now and ask a specific question about a specific number, is there any particular number anyone would like me to go over now?
Would you be able to go over 94?
You bet. Let's do that. That's actually a much better way to do it, because if I go through this sequentially again, it's going to bore us all to tears. Let's do 94. 94. A simple TTL decoder can be used as an instruction decoder. So here is the essence of the creation of a CPU, right? So this computer architecture class, we ought to be able at the end of this to know something about what's inside of a CPU. So here is an instruction decoder, and it is a 74HC138. So HC, does anybody know what that stands for? So herein lies the interesting thing about the Google, in case you're wondering about something like this. Type in 74HC138, and you will find out that this is a high-speed CMOS decoder. You may never have seen one before, but this is what they look like. We actually have these things in the shop. You can get them in the dual inline package. The dual inline package is good in the sense that you can put this using its little legs, which are on 0.1 inch centers, directly into a breadboard so that you can use it for prototyping. But if you want to manufacture, the electrical functions and the pinout assignments are identical for the small outline integrated circuit that you see here to the right. And so what that means is you have a surface mount that is a low-cost mechanism for creating this technology on a printed circuit board. In the event that you're real interested in learning more about the data sheet, you could click on the data sheet, and presumably that just downloaded, and there it is. And now it tells you, aha, it's a 3 to 8 decoder. Now, 3 to 8 decoders are not new to you. You have seen these before. It's a demultiplexer, so you know about muxes and you know about demuxes because you took Digital Design 1. But now we're going to take 3 bits and make 8 indicators come out. So here comes the 3 to 8 nature of the decoder with a few different enables going on here. And you can see it's got inverted outputs. And if you remember anything about the Digital Design 1 class, you remember that you can use a NAND gate, and that the NAND gate will cause this to give you a canonical sum of products, right? So in other words, you can take these outputs and run them into the NAND gate inputs selectively, and those will be the product terms that you'll be adding. So this essentially enables you to create a function of 3 variables, and you can use that function to, with a NAND gate, and you could have several NAND gates. So you've got fully decoded min terms here. That's the proper way to say it. And here are the min terms coming in all inverted. When you use the NAND gate, the bubble propagates through the NAND gate to make an OR gate and then inverts the outputs. And so this becomes a NAND gate turns into an OR gate using De Morgan's theorem. So that's the upshot of all this. Now you know what a 74 HC138 is. Apparently, there's another variant here called the HCT. And if we read through this data sheet, we'll see the difference between high-speed CMOS and HCT. But in any case, let's see what they say. Same, slightly lower voltage. For a maximum anyway. Slightly higher voltage for minimum. It looks like the temperature range is the same. It doesn't look like it's particularly different in speed. I don't know what the difference. I never heard of this T variation on the. Oh, it's temperature. High temperature. Look at that. It goes to 125 degrees C. So this is the high temp version that'll let you deploy it in a high temperature region, I guess. Looks like that's the only difference that I can see. The current, it draws a little more current. Very little. I mean, the difference between 80 and 160 microamperes is 80 microamperes, and 80 microamperes isn't going to break your power budget. It looks like it's a little bit slower, but not by much. 30 nanoseconds. So that's interesting. I mean, it's got some small changes in speed, but it's got the very high tolerance in temperature. HCT, high temperature tolerance. I didn't know that. How about that? That's a variation I never encountered before. We do not have HCT in the shop. So now you know what that is. That's kind of interesting. So now what's going on here is this instruction register is really little more than a bunch of flip-flops. And it's presenting the two of the HC138s. So that's giving you 6 bits on input. And then it's allowing you to decode the instruction that's going in and choosing what you want to do. Invert buffer, clear buffer, activate the adder. Let's see, load into the accumulator register. Let's see, put it, activate the RAM. All these different instructions can activate all the different subsystems. So this instruction decoder is, well, nothing more than a 3 to 8 decoder, and there's 2 of them, so it becomes a 6 to 16 decoder. So that's interesting. And so the answer to that is true. I could have just said, hey, the answer is true, but maybe it's better to explain why. So they're building a CPU. This is probably a trivial RISC machine that will essentially be constructed out of transistor logic, all hardwired. Cool, right? So then what's the other question? Any other questions? Any specific questions you'd like to ask? I will answer any question you want to in class, but outside of class, you're kind of on your own. So this is your time to go through the test and sort of decide whether or not you have any questions. This is a Richards controller, the 74163. That's a ripple counter. 151. What could that be? Well, it actually says it right here. It's a multiplexer. So that's a 3 to 8 mux. And the 7442, this is a BCD 2 decimal decoder. So there's another decoder giving you the various functions. So this becomes a controller using a 3 to 8 decoder. Well, is it a 3 to 8 decoder? Could we have used a 3 to 8 decoder instead of a BCD 2 decimal decoder? And the answer is false. And the reason why is because you got a lot more functions with the decimal decoder, and you got 4 bits worth of input in here. But one of the bits is coming out from this multiplexer, and the other bit activates the other decoder. So that gives you a whole bunch more functions. So, no more questions. Should we go to the beginning and just sort of zip through the test from the beginning? Would that be a reasonable thing to do, folks? I leave it to you. We could start from the end. We started from the beginning before. We could start from the end and work our way backwards. How's that? Just to be sort of different. Although I think we've seen these things quite recently. What do you think? Start from the beginning or start from the end?
You can mix it up and start from the end.
Start from the end? All right, then. That's what we'll do. So we've got this microcode question. The following is a microcode control unit. You look at this and you go, what the heck are they talking about? So I don't know if you guys have ever tried Googling microcode, but there's like a wiki on it. And it is a programmable mechanism inside of the CPU that allows you to change the state machine. And they say it's firmware, and it resides inside of the CPU and allows you to alter the instruction set. But if you're going to hardwire everything with TTL and an instruction decoder, well, it's not microcode. Let's see. I'm going to just sort of zip through these things. Question 99, questions? 98. This is the block diagram of the TTL system we were just examining. This is Harvard architecture because it's got separate data memory from program memory. We just took a look at the Richards controller here. And there's the 138. Now, is that a 4 to 32 decoder? Well, we happen to know it's not because we just looked it up. The 74138 is really no different than the HC138. It's just it's not high-speed CMOS. It's low and slow. Low speed. High power. Takes more power. Let's see. We got jump questions, branch predictors, Flynn taxonomy, marshalling, translate look-aside buffers, threading. Oh, here's question 88. In Java, when we create a new thread, the thread begins to run. Is that true or false? Anyone would like to guess on that one?
False.
Yeah, that is false. It's just ready to run, but it doesn't run until the scheduler gets to it. So, let's see. So here's a thread made with Hello World. Here's a simulation of 1D. Well, a simulation of two-dimensional arrays using addition and multiplication. Let's see. Here's serialization. Row major versus column major. I think we got bored with that one. Routers are the same as switches. Oh, that's, from a networking point of view, that's certainly not true. Public interface, computable object extends. What is returned when a computable instance is passed? Well, you can see something is serializable. But is it a computable object? What is returned when a computable object instance is passed? This is question 80. Anybody have any ideas?
Can you scroll down a little bit?
Yep. That's a very good point.
It's the serializable type, the last one.
There you go. That's it. So then here comes PowerPC execution flow. I don't know if I'm going too fast here. There's the vector unit in blue. That's a vector processing unit. A network switch is the same as a MAC bridge. What's MAC stand for? Have you not heard of a MAC address?
Is it medium access control?
Yeah, it is correct. So media access control addresses are generally unique, although this is a very interesting point. You can clone a MAC address in your router. And once you do that, you can fool the internet service provider into thinking that your router hasn't changed. So if they've assigned you cable modem, a IP address, and all you do is clone the MAC address from the prior router when you upgrade your router, it won't know that you've changed routers. And so your IP address doesn't change. Isn't that cool? So MAC addresses can be set. They don't have to be unique. But if you have two devices with the same MAC address on the same local area network, you're probably going to crash the network because you won't know how to route the packets, and things will just die horribly in flames. Let's see. Multicast datagram sockets useful. I guess that's obvious. In networking, a packet can be sent to. I shouldn't say it's obvious. Look, if you got a question, I will cover it. I've got networking, TCP, multicast datagrams, use UDP. More multicast questions. Another multicast question. Multiple processes. I guess we did everything, but if you've got a question about it, we'll do it again. General purpose microprocessor. Marshalling. And here's loop unrolling. I think part of the reason I like to go through it again is just to make sure the formatting is right and everything that has a picture or is supposed to have a picture has a picture. We've got the principle of locality, more threads, concurrent programming. Layer 2, that's the data link layer. Multicasting, interrupts. Well, that looks interesting. That could be a microcontroller for all I know. It's got everything: RAM, ROM, I/O, timers. It's got everything on a chip, it looks like. That has the look and feel of a microcontroller, self-contained computer on a chip. That's actually a fairly good point. I don't know if you've actually seen some of these Arduino systems. Right, this is how it started, with a chip and a little crystal and an interface to the USB. But pretty soon people said, oh, this is too complicated. And so then they came out with just the chip with a little crystal. And they said, well, how can we make this even smaller? And so then they said, well, make the nano and we'll use the micro electronics packaging. And so then this became a full-blown computer that you can actually get very inexpensively. And that's kind of a nice way to go. And then they made the Arduino. I like this guy. They just took a little dip and they mounted a circuit board. And then they just said, you know what? We're going to solder the pins that come out of the bottom of the circuit board straight to the pins that come out of the chip. And they did that. And I don't know. They made something cute and ugly all at the same time, and perhaps even fragile. Certainly this looks like it's suitable for an embedded system like a drone or something. This guy, I don't know what you would do with that. Goes on a breadboard, so that's convenient. Right? Plugs right in. That's good. I like that. Like a breadboard. But where's the USB interface, right? Well, you got to add that on the side because it doesn't have one. And then once you're done, you can take that away, and then you're just left with this ugly looking header sticking at the top. And at the end of the day, all you need is the little programmer port that sticks out on the top, your dip. I don't know if you need an LED, but it's nice to see if there's power. A reset button, a cap, and a resistor. Crystal. Another cap. There's not much here. Oh, another resistor. That resistor is a current limiting resistor for the LED. You probably don't need either of these things. So that's a full-blown computer. You really RAM, I/O, timer, CPU. That's the whole shebang. So that's a microcontroller for you. Multicast groups. Let's see. Guys want to look at pipelines again. And here's a floating gate that stores bits. You know that this style of creating a non-volatile memory has gotten very dense. So you can get many, many gigabits or gigabytes even on little SD cards or flash drives, all done with these sort of floating gates. There's that Flynn taxonomy again. Datagrams. Datagrams are important for multicasting. Here's a multi-stage pipeline. Let's see what else we need. Here's a little microcontroller. It doesn't show the I/O. Oh, it shows peripherals. I guess that's I/O. Here's the cat's picture. I hope this came out for you guys. But in any case, it's figure 1116 in cats. I found this on the web, and I put it in there, and then I put this in the web. I don't know if that fixed it for you. Are you getting a picture for question 51?
We have one of them.
You're good. You're good. All right. We only need one. Let's see. There's a virtual address space mapping to physical address space. Virtual memory. Daemon threads. I think I revised this question. There were several questions that had bugs. I went through and tried to make sure that we debugged the final. Synchronized. Multi-threading. SMTP. Server sockets. More information about ports and SysD. SIMD. And multicasting. I got layers, layer questions, OSI layer questions, routing questions. More information about NOR versus NAND flash memory. Member interclasses. Superscalar. What else? SysD versus MISD. Loop fusion. Loop unrolling. Oh, this looks, didn't we just see this? I think we got a duplicate question here. Oh, that's all right. It's a gimme. IP multicasting. Am I going too fast? CUDA cores. Flash memory. I think we're getting to the end of it. Neumann architecture, Amdahl's law. And that brings us to question 1 on threads. So you guys tell me, did you have any other questions about this test? So what did you think about the distance learning this semester? Was it all right?
It was a little challenging at first, but I feel like we all got used to it.
Good, good. Yeah, I myself prefer to teach in the classroom with students. I don't normally like to go and sort of run through tests and go through all the homeworks in the way we have done. It's not my style, as you know. And you've seen me teach Digital Design 1. This is definitely not my style. And I don't know what's going to happen with Digital Design 1 next semester, because this is going to be, I just don't want to go through the process of, tediously running through homeworks and that sort of thing. So maybe I'll try and do some more pencil and paperwork. So that's where we are. You've got 7 days in which to finish this. Please don't wait till the last minute to do it. Better to get it done now before finals week, and free up your time for other things, I think. So that's my thinking, anyways. And if you have a problem, I have time to get you unstuck. There's not going to be any extensions after the 1 week period is done. So it's due when it's due, and it's the end of the semester, so we can't just have it go on and on and on. So do me a favor, start your final early and get it done, get it out of the way, get it out of your hair. If you have any questions, I'm still here, so now's the time. No more questions? So listen, it's the end of the semester. I want to wish you guys a great break, a Happy New Year and a Merry Christmas, and the best of luck on your finals. Stay safe and enjoy the rest of the day, because I don't have anything else for you today except to review the final. That was my lesson plan.
Thank you, Professor.
Thank
Thank
you.
you, Professor. Have a good break.
You too. Have a good break.
You too. Thank you, Professor. I do hope that I'll see you on campus soon, but in case we don't meet again, you led an amazing class this semester.
Oh, thank you so much. That's very kind of you to say.
Yeah,
Thank
no
you.
problem. It's the truth. You did really well with this and digital design, and funny enough, both of them went online towards the end of the semester, but hey, you still did it pretty well, and I ended up taking a lot out of the course.
Cool. I appreciate hearing that. Thank you.
No problem. So again, hopefully I'll see you in the future, but again, thank you for this semester.
Sure. Thank you. Bye-bye.
Yep, bye.